Hello everyone, I am Lot. For those of you who don't know me, I have finished my PhD no more than a year ago at this point at the University of Sabatier in Toulouse at the last laboratory where I was working on in material science, more precisely numerical material science. And in particular, my topic of research was the developing of machine learning potential for silicon to investigate the phenomena between the diamond structure and amorphous structure, the interface between diamond and amorphous structure in crystals. After my PhD, I arrived directly here, where I, starting from the position of being a HPC user, I became the maintainer of an infrastructure. And which is the infrastructure? Well, this talk is going to be a little bit more technical. I hope I won't bother anyone. The infrastructure that we're going to talk about is ORFEO, which is the data center that is here in area in Basovizza, to be more precise. That is composed more or less from between 50 and 60 computers that are divided into different categories. We have those that are used for the computational side. We have divided in different categories of our architecture. We have the Intel one, the AMD one. We have those that are empowered with accelerators, a little bit older, newer, and allows you to perform any kind of calculation that you want within the boundary, within these computational boundaries, obviously. On the side of the computational hardware, we have the infrastructural hardware, we have the service hardware where we offer Proxmox services, which is virtualization technologies. We have Kubernetes nodes where we run infrastructure as a provision, essentially, resources to users. And storage system, for the storage system, we have a distributed one that is composed more or less of 12 nodes, and this offers different qualities of storage. We have the level 1 or the fastest kind of storage, which is the SSD or NVMe one. We have the second level or HDD standard hard drive, which is a little bit slower, but nevertheless very performant. Then we have the an NFS system as a way to distribute data on a even slower, with an even slower piece, but in this case, we can offer a much higher capacity at a smaller cost. And finally, more to come, we are working into setting up a tape station, a tape library, which is a device that can store your data into tapes at a very low maintenance cost and very small impact on the side. Now, recently, as you may all know at this point, this infrastructure got founded by two separate projects. We have PLP, which is the one that we are here for, and then FFIDI on the other side, which is the one from specific for material science in collaboration with CNR. Both those projects needs for an IT infrastructure that must be flexible, stable, and secure. While flexible is because of the researcher. Researchers have codes that run on different hardware that have different requirements in terms of memory, and the structure needs to be adaptable to the requests that we get on a day-by-day basis. And these can get quite wild sometimes. And then we have the stable part, because there are some experiments that are not that have some pipelines that are very well defined, okay, and the researcher need those pipelines to be run on a regular basis, so we cannot fail them in a certain way. And then there is security also. That's another topic that should require his own presentation, even though in high-performance system, often we thread security for performance, which is one of the things. So let's start by trying to understand which are the requirements of these two separate projects to define what we need in order to satisfy them. And both these projects have the experimental online computational needs in different ways. So the material science, both will acquire some electronic microscopes, okay, which is this is the cryo-EM, the one of specific for PRP, but they work in a very similar way. There are some cameras. Cameras are connected to central computers. Those central computers do not have the computational power to perform online analysis of the stream of data that is coming from the cameras. So those data are stored into a local server, and possibly they are offloaded in real time towards the facility, ORFEO, in this, that will be ORFEO in this case, where the online analysis is performed and is fed back to the control PC, where the researcher can see what's going on inside the microscope and, for example, focus it better. Okay, this is the most standard kind of online analysis that people can do. If this online analysis is not possible, we have to think a little bit later on a more broad spectrum, because maybe the resources are not available while the microscope is running. So we need to have some storage set up in order to store the data that cannot stay in the local server. Just to give some order of magnitude, this machine can produce something like 5 terabytes every 24 hours, 5-6 terabytes of data every 24 hours on an average day. I have talked with people that were able to push it to around 20 terabytes a day as a maximum capacity. So if we cannot do this online analysis, we need to set up a storage that is able to absorb those data and then post-process this in a second moment. And this goes for the experimental computational need. Moving on, we have the, sorry, keep going in the wrong direction. We have the standard researcher computational, or not standard, like standard from my point of view, where you are the computational scientist. And in this case, you have two separate ways of accessing your the infrastructure. You have your delayed job, where you submit your job and you wait until it will eventually get systemed into the it will get scheduled by the schedule system and it will run on the infrastructure. Or you have something like an interactive session, which is becoming more and more popular among the PhD students, especially, where you run your Jupyter Lab, your Fire App, and you would like to have it immediately running on the HPC infrastructure, which is quite challenging on its own, since this kind of infrastructure is born with the idea of performing operation all day around and not having them the resources ready available for you to be used at any time you want. Finally, we had the presentation before about the FAIR principles and how do we want to verify all the laboratory and so on and so forth. And in this particular case, we have again a situation that is very similar to the one that we saw with the electron microscope that we were discussing before. But instead, what's happening, this is more of a broad problem. You have the researcher get to a laboratory. In this laboratory, should be able to access his own data, should be able to, why does it get to a laboratory? Because he does not have the instrument in his own laboratory. And so he gets to another one to perform the operation, to perform the experiment, and then he gets back home and wants to analyze the data. And you need a storage, common storage that is accessible from both positions. Okay, in this particular case, we're a little bit more advanced in the study, at least of the infrastructure that we want to develop, thanks to the NFF RDI that started this way for PRP. And in this case, what we are looking for is to essentially separate the different parts that are involved into the managing of this situation. We have the identity management system, that is the system that that tells us who are you, essentially, and this should be institution dependent, because the institution where the researcher is coming from that should tell us who is he. Then we have the proposal manager, because if he comes to another laboratory, to another research unit, it must be under a certain project under a certain proposal with a certain task to perform and so on and so forth. And with within NFF-RDI, we were thinking on a schema of something like this, where you arrive in your laboratory, you get to the interface, you get your interface that collects information from the different sources and allows you to access certain experimental instruments. And once you acquire data from the experiment, you can store it into a notebook, which is not a laptop, it's an electronic notebook. And then this information gets moved to our storage that you can access remotely from your laptop, from your laboratory when you get back in your institution. So to develop all of this, and this is where our talk will concentrate, what our talk will concentrate on, we have to develop development platform. I mean, it sounds a little bit tricky, but to be able to test the integration between all the components that goes on to solve these three problems that we just saw, you need to have a development platform. And what I'm going to talk about is which are the main components of this development platform, how are we using them to perform the development, and what are we going to do next. So let's start with which are the main components. And in this case, the fundamental building block is a virtual machine. So we have the hardware. We cannot use the hardware in order to test our integration, because this will stop what people are already doing on such hardware. So I will basically kick you out in order for me to perform my job and keep evolving the infrastructure by itself. And for this tool, we went for, so we have virtual machines. This is a little bit technical, I realize now, but essentially what we went for is that we have our kernel, our Linux kernel that you all use. On top of it, we have a KVM infrastructure, which is kernel virtual module. That is modular. It's a modular approach and adds some extra extension that allows external external machines to perform operation on the kernel itself and access the resources below. Then we have QEMO, which is an extra software that allows you to virtualize the device, like network interface and so on and so forth. libvirt, which is the thing that orchestrates everything we just said. And finally, for the final user, we have Vagrant, which is something that simplifies everything else below this layer. The information we want to give you is that even working out how to develop an infrastructure, to test an infrastructure, is not as trivial as it sounds. Okay, there are many parts that are involved, many software that have to work together, and this will be the leitmotif of this presentation. So there are some cases that they wanted to outline, like that we can virtualize at all, which are the exotic part of the hardware that we have, like GPUs, or for example, the InfiniBand, which is a kind of connection that HPC nodes work on. Those we can't really simulate it. So if we want to use them, we have to block resources, real resources that can be better used in other case. And on top of this, we have a thick layer of Ansible. What is Ansible? Well, Ansible is synonymous of automation, and it encodes the technology needed to deployment a certain service or perform a certain operation. In particular, Ansible is divided into what are called roles, and this information is encoded in roles. And we have developed several roles for the different part of the software that you are using on ORFEO and that we test continuously on our testing the platform. SLURM is the most common one that all of you might know, and we'll come back to that later. Then we have the modules, driver configuration, and we have Kubernetes. Kubernetes is another layer of infrastructure that is needed in order to run the whole system, where you deploy your software in a more elegant fashion. Let's say Helm is nothing more than the packet manager of Kubernetes. So Helm stays to Kubernetes as Ansible stays to your regular hardware, if you want to put it that way. A little bit out of context, I will put the slides because I think it's worth mentioning because it came up more and more. So from a business perspective, what are we? Okay, we as ORFEO, as LADE, we work fully on premises, so everything it's managed by us. We start from the server, from the hardware itself, down to the application. When we include on top of this all the elements that I showed you before, so all these elements that I showed you, kernel, KVM, QEMO, and libvirt, then we move from being on-premises service to an infrastructure as a service. So we manage for people the server, the storage, the networking, the virtualization, and they are able to install their own operating system, their middleware, their runtime. And we do this on a regular basis. We do it for us because we have to develop the testing infrastructure. So we offer it as a service to us, but also to external entities. For example, the services that we offer into the NFFIDI ecosystem for example, are offered as a infrastructure as a service. Then we have SLURM on top. Okay, so to get this queue manager system, we have to add the operating system, which we have to install and maintain. We have to add the middleware, which is SLURM, and there is no runtime in this particular case. And then, or instead, we can add Kubernetes, which has its own runtime, and then we move to a platform as a service kind of offer, where you have to bring your application in the case of the scientific code, the code that you developed, or in the case of Kubernetes, the application that you have developed, the web application or whatever you have developed. And you can run it on top of our infrastructure. And then there's the final software as a service, which is where we are going when we will come back to the example of the laboratory and the student and the researcher that goes from one laboratory to the other, where we manage the whole full stack at every level. How are we using this development platform? Well, as I said before, it's mainly for testing purposes, but let's start from the basics. I promised to get to the software that it's behind the scene, and here is the first one, the most common one. It's SLURM. SLURM is a resource manager, so it's the one that gives you basically access to part of the infrastructure when you ask it. And the development of it's mainly a problem of compatibility metrics. So you install SLURM, okay, it depends on several libraries. We have to test them before rolling out new updates before changing the operating system and rolling out the security upgrades and so on and so forth. And this can only be done, and this can be done without affecting you essentially in this testing infrastructure. Some of the most common components, for those of you who are keen to know, are PMIX, UCX, and VML for NVIDIA GPUs. And we keep developing policies. I mean, as you may have seen in the last year or so, we keep rolling out new policies that we have first tested and verified on the test infrastructure. And for example, going back to the first slide and to the need of the EM electronic microscope. Okay, there is one problem that we have to solve now, and we are trying to solve it within this development environment. That is, the electronic microscope. It's running at a given time. We have to make the resources available for that electronic microscope to run when it is on. I mean, we cannot wait till we cannot wait for the other codes to stop to end their run. So we have to find a way, and this is a thing that we have to test, to move out to take the RAM that you're using, take all the state of your code as a regular researcher that submitted this asynchronous job, put it on the side, run the pipeline of the instrument, and then place your code back. And this is the kind of integration that we have to develop. On top of it, I'm running out of time. On top of it, there is the identity management system, okay? And this comes from it's clear in the case of the researcher that moves from one place to the other, but this scales to a much more deeper level, because when you connect to the login node, for example, of our infrastructure, we need to know who you are. We need to check your password. This must be consistent all around the infrastructure. This might be, in principle, not provided by us, but by your institution that you are part of. And this comes with its own set of complications. There are like thousands of softwares and libraries that are involved and need their own configuration, and it's not equal for every kind of machine. And the more the variety of the machine that you have, the more the variety of software that you need to maintain these machines, and the more complicated this becomes. Then there is storage. Okay, storage is another topic that I find very amazing, because people still think that it's like your laptop. I mean, you plug in an hard drive and it's working, and that's not exactly how it works. In our case, for example, we are using CFFS, which is a distributed file system. So when you put a file on your home folder, this file gets split into separate objects, and those objects get placed in an abstract concept that is a placement group, and these placement groups insist on over a pool, and this pool is defining the level of risk, let's put it this way, that we are able to accept for your data to be lost. And there are different policies. We have, for example, for the home, we have 3 replicas of your data in different machines. Instead, for the Scratch folder, we have 8+2 kind of distribution where your data is split into 8 parts, and then we compute the checksum of we compute 2 checksums, with which we are able to reconstruct your data, 2 parts of your data if we lose it, for example. And it has a failure domain, and this goes with a failure domain. That is, how much of our infrastructure are we able to lose before losing your data at all. And in particular case, we have our failure domain usually is the machine, so we can lose up to 2 machines before losing your data. So it's an advantage of distributed infrastructure. And even here, going back to the idea of why do we need a testing infrastructure? Well, we have to test if this is working. I mean, we have to have 3 machines, and we have to turn one off and check that our configuration that we have deployed is actually saving the data and not crashing everything. So moving on, Kubernetes. Okay, I will leave this aside because it's another complicated system like SLURM to manage workflows, okay, of a much higher complexity, where you can essentially declare the states that you want. So you have let's say from a broad perspective, you have this software that orchestrates for you smaller pieces of software. Okay, so you have your website. Your website needs different components to run, and this orchestrates all of them and offer a complete service to the final user. And it comes with all its quirk, all its libraries, all its dependencies. It's basically another infrastructure inside your infrastructure that you need to manage with all and it has to integrate with everything that we have discussed before. Okay, so where does this Kubernetes gets important? Well, it's in the development of the laboratory environment, for example, where you have the identity management, that is the software that we saw before, complex set of softwares that we saw before, and those, for example, can be very well integrated into Kubernetes and can be managed by it instead of by us. There is the proposal manager, for example, in the case of an FFABI is already an NFFA EU, which is the project that was before FFABI is already managed within Kubernetes, and the whole laboratory set of components that we need to develop would be very would find their natural home, let's say, in such a kind of infrastructure. Okay, so like the interface, the notebook, the storage will be outside, obviously, because it will be chef in one of his flavors of file systems. Can you play with it? Yeah, this is a nice thing. Yes, we recently, thanks to many of you, we recently published the whole piece of code that you need to install and compile and so on and so forth in order to run it. What are we going to work on in forthcoming future? Well, we have the, let's say, small kind of objectives, which is the 100 paper cuts program, which is a thing that is this approach that made Ubuntu, for those who know it, famous for what it is. Essentially, they took all the small problems that were there. None of them was highly challenging, but they fixed in one after the other, and they obtain a polished experience for the user. Then we have the user management part, so the integration with different identity management. The monitor system, for example, is another topic that I haven't touched about. All the infrastructure need to be monitored all the time, and that's an update. That's a topic we are actively working on to updating it. Then we have resource control, migration policies, because sometimes problem happens, bad choices are taken, and some OSs some OS that we have decided to deploy, for example, does not support any more software that it's really needed in order to perform a certain operation, and we need to find a way to migrate from the old operating system to the new one. And how do we update how do we keep the infrastructure up to date in all its parts? On the let's say on the longer term, what it's nice, I mean, what we are looking for is moving towards the declarative infrastructure. That is the paradigm that was trying to introduce before with Kubernetes. That is, if now someone comes and asks for a specific tool, we need to decide, we need to reshape our whole infrastructure by hand, by someone doing it, in order for that tool to work, to let's say integrate in the grand schema of software that is present. The idea would be to encode this knowledge into the Ansible structure that I presented at the beginning, or in the Helm chart that have been a bit presented, and being able to simply declare what we want, and by the mean of all the information and the procedures that have been encoded into the different parts of the underlying structure, obtain that for free, essentially. So someone arrives, tells me I want this, this, and this, I just add them to the infrastructure, and as long as I have a way to have those deployed, those will get deployed everywhere. Then we are investigating the HPC foundations, so it should be S, because by tightly working with SLURM and Kubernetes, we realized that they are not that much of a difference. I mean, they are two sides of the same medal. They use the same core concept to achieve results that are very similar. And in particular, SLURM is a subset of features of Kubernetes. Okay, so the code that we regularly use to submit jobs and so on and so forth is just a small set of a bigger one. It's just that the second one is not thought to work well. I mean, it does not have in mind our kind of workflow. So it would be interesting to investigate if it is possible to completely get rid of SLURM and just live with the second. And then greenify the infrastructure, because we have to draw less power and know how the power is used all around the cluster. And thank you for your attention.